Welcome everyone. We're here for the workshop of the cost model and performance with Zach, and I'll let him take the stage.
You just start sharing my screen. Okay, hello everyone and welcome. My name is Zach Burns. I go by that 3% on GitHub and on Discord. The name that 3% is a reference to an obscure Donald Knuth quote about performance for computer science geeks. It's not to be confused with a reference to the political group having a similar sounding name. So today we're going to be talking about cost models. First question is, well, what is a cost model? What is it for? Why do we even have this concept? The problem is that an indexer needs some way to express to a consumer like the gateway that what the fee is that they're going to charge for a given query. Not every query is equal. In fact, some subgraphs have greater costs to index than others. Some subgraphs can better amortize those costs over higher query volumes. Some subgraphs may be very competitive and have competitive pricing because maybe they have a lot of signal and there's a lot of indexers competing for queries on that subgraph. Some might not. And even within a single subgraph, one query may take a dozen milliseconds to execute and another may take several seconds to execute. Even beyond the differences of subgraphs and queries, not every indexer is equal either, right? An indexer which invests in a low latency database or invests in economic security, maintains an excellent reputation, or attracts delegation through their community involvement, they can and should charge a premium for the better service that they offer. Broadly speaking, there's a lot of factors that can go into the fee for a given query. So a consumer, like the gateway, has a query and they have a choice to make between the many indexers and it would like to pay a fee for that query that is going to be fair for the level of service that the gateway requires or the consumer requires given the current market conditions. So the question is that how might the gateway approach this problem of finding out what indexers are offering to serve that query for a competitive fee? So one way to do that might be to expose an endpoint on the indexer, say get price for query. That API could take a query and then return the fee that is being proposed by the indexer. A gateway could send their query to each indexer that's indexing a subgraph and get the feedback for all of them and then compare. This has some problems. The first problem is going to be that it introduces latency into the query. So an end user who's waiting for data to load in a web page would usually have to wait an additional amount of time for those fee proposals to come back. In practice, this wait time is always going to be the maximum amount that we're willing to bear because some indexers will probably have latencies that exceed the maximum wait time and where we'd be waiting for some set of responses to come back, and that would add a lot of time that the user spends waiting for data. So that's not great. And then the other problem with that is throughput. While any competitive indexer may expect to receive many queries, for any given query, only one indexer can be selected. So that means that the vast majority of indexers are not selected for that one given query, and sending unused fee proposals around is not going to be an efficient use of the bandwidth that's limited, available between the indexers and the gateways. So this is where cost models come in. You can think of the cost model as basically a price sheet that lists all the queries that an indexer is willing to serve and for what fee. And so the assumption is that the gateway will be able to serve many queries to any indexer on average, and it pays a higher upfront cost in performance to request that cost model. And then when the query shows up from the end user, to pay a much lower performance cost just to look up the fee given the cost model that's in hand and periodically update the cost model out of band. So that's sort of the design motivation behind cost models and what we're thinking of when we designed it. So here's what a basic cost model looks like. To express the cost model succinctly, we developed a language which is called Agora. And you can think of Agora as essentially a price sheet. It lists all the possible GraphQL queries that you might serve on the left, and all the fees for those queries go on the right. We can break down how that looks for this specific simple cost model that's in front of us right now. Paying attention to the box on the left that's labeled Agora, we can see a simple GraphQL query, which is for swaps. I'm just using Uniswap here because that's a very well-known name in the DeFi community. So it says we're going to ask for the GraphQL query of swaps, which is followed by a fat arrow, and then the number 0.01, and finally a semicolon, which terminates the statement. Continuing the price sheet analogy, the left side of the fat arrow is the service that you're offering, in this case, the GraphQL that you can serve. And the right side of the fat arrow is your query fee in GRT. So in the Agora terminology, right, leaving the terminology of price sheets for a moment, this query fee listing is called a statement. The left-hand side of the statement is called the match, and the match tells you the set of queries to which the statement applies. And the right-hand side of the statement is called the cost expression. The cost expression evaluates to the price of the query in GRT. In the examples box, we're going to have some queries and the prices that they would evaluate to. You can see from the examples that the Agora query in the box labeled Agora that's in the statement is the most general form of the query that matches. So in order to match, every part of the query specified in Agora must have a corresponding item in the real query. So walking through the first example, you can see that it asks for swaps and the ID field of those swaps that it gets back. And that will match our Agora cost model because the Agora cost model is only asking if they have swaps, and that first query does. So it matches, and therefore the price of that query is going to be 1/100th of a GRT. The second query in this example also matches, even though it's specifying an argument for the first 10 swaps, and it's also asking for the transaction instead of the ID. That also matches because our Agora cost model only specifies that it must include swaps to match. And so that also ends up being priced at 1/100th of a GRT. And then the last example is asking for mints by ID, and that query gets no price, so it's not going to be served by the indexer. It just does not match our cost model. All right, in Agora, a document is going to be a list of statements, right? To get past that problem of some of our queries not matching, we can provide more statements to our Agora cost model. The statement priority is going to be from top to bottom. So given any query, we're going to try executing each statement, and if it does not match, then we're going to continue to the next statement. And if it does match, then we're going to evaluate the right-hand side of the expression to find out what that price is. So that means that your cost model should order statements from the most specific to the least specific. And I have some examples here that's going to show how that works. All right, so just walking through this to be fairly pedantic about it. Our cost model is specifying 3 different statements. The first statement would match any query asking for at least swaps and the field transaction. The second statement is asking for any query that asks for at least swaps with the specific argument asking for the first 10 swaps, and that has a different price. And then the last query is the least specific one, and that's just asking for anything that has at least swaps, and that has a price as well. So in the examples, the first query is asking for swaps by ID. We can check each statement in order to see if it's going to apply. So the first statement in Agora is not going to match this query because that statement's match is specifying the transaction selector, but our query is asking for the ID selector, and it does not have the transaction selector. So so it will go on to try and match the second statement. The second statement also does not apply because that statement is saying to match an argument for the first 10 swaps. And the query swaps by ID doesn't have that argument. But the last statement does apply because that statement's match is only specifying that it needs to ask for swaps, and the query does ask for swaps. So this query is going to be priced given that final statement for the price of 1/100th of a GRT. We can execute that same process on the second example query, which I'll go over that one. It says we're going to ask for swaps with the argument first 10 and then ask for the transaction field. Looking at our first statement, we see that we are indeed asking for swaps, which the statement says that it must be asking for swaps to match. And then we must also be asking for a transaction to match. And our query, the second query in the examples, does specify, yes, I want the transaction. So that's going to be priced using the first statement for the price of 2/100ths of a GRT because it completely matches what's being asked for by Agora. Now GraphQL is very flexible, and there's practically an infinite number of queries that you might serve. So it would not be a very good idea to try and list every permutation of a query in Agora. So we have a way to, instead of listing individual queries, to extract the relevant features of a query and then derive a price from that. So the first statement in this slide is an example of that. I'm just going to walk through the syntax here. Instead of saying before, like on the previous slide, that we want swaps with the first 10, it instead captures that argument using the GraphQL variable syntax and says the first colon and $ first. So that will take any value for first and then capture that value so that we can then use that value later in the right-hand side in the cost expression. So given an example here, it says if we want the swaps, first 100 swaps, get their ID, the way that that's going to be costed is to run that first expression. It's going to match on swaps. It's also going to match on this argument that says have the first argument, and it's going to then capture that 100 into the variable first. Execute then the right-hand side of the cost expression, which says I want a base cost of 1/100th of a GRT. And then I want to also charge for the number of swaps that you're returning with a cost of 0.0002 GRT multiplied by the number of swaps that you're returning, multiplied by that first argument, which is going to be how big the list is of the swaps that is being returned. So in this way, you can scale the value of a query or the difficulty of the query by extracting the relevant features from that query and then using it in your cost expression, right? So in that first example, we can see that if they specified first 100 and then capture the ID, that's going to resolve to a price of 3/100ths of a GRT because that base price 0.01 plus 0.0002 times 100 is that price of 0.03 GRT. This next example here says swaps by ID. It's going to run the first statement and find that it does not match because it does not specify that first argument, and go on to the second statement, which says that swaps without a first argument are going to be priced at 0.03. This is not coincidental because the default value for first in our GraphQL queries is 100. So it ends up resolving to the same price as the previous example, which was asking for the first 100 elements. If we left that out, we get swaps by ID, the price 0.03. And then the third example is asking for more results. It says swaps first 1,000. And if you run that, you'll get the price 0.21 GRT, which is going to be a greater price because they're asking for more data. That is captures, and that's one of the language features. One thing is that if you're like me, you probably don't think in terms of GRT. You probably think in your local stablecoin. So one of the utilities that we provided for you is to be able to inject the value of DAI into your cost model, which is an approximation of the value of a US dollar. So if we wanted to have a query that is priced consistently at half of a penny, then what we could do is we could take the value 0.005 and multiply that by DAI, which is a global variable that I'm going to go over more about what that means in a minute. But it's going to correspond to the conversion rate that would convert from DAI to GRT. In this case, this DAI global variable is a bit magic because it's automatically injected by the indexer agent by default. Your indexer agent will look up a price that it thinks is a good swap rate for DAI to GRT, and then it will inject this. So in that way, you can respond to changing market conditions very quickly in your cost model without having to go in and then manually tweak a cost model. Generally, that's what global variables are for. Let's see here. I'm gonna go ahead. Well, I guess there's a quick example there, which went by really quick. I'm gonna just go over that. So in this case, that example query of asking for swaps by ID, it would evaluate to 0.5 cents, half a penny, as we anticipated. All right, so globals generally are there for you to be able to respond to market conditions very quickly. So you can update any information that changes over time that you'd like to respond to automatically. But unlike the DAI variable, you're going to have to write your own script to collect that information and then update the globals JSON yourself and provide that to the indexer CLI. So some examples of that, just to give you some inspiration of what you might use it for. It's going to be totally up to you, but these are some ideas. The first statement says that if today is discount Friday, then you're going to apply a specific price for all queries because it's the first statement and it's matching all GraphQL. So going over that, it says the first word in that statement is default. That means match all GraphQL. And then the next word is when, and that means to also apply this condition. In addition to matching the GraphQL, we also have to make sure that whatever this condition is, that it evaluates to true. And then you see $discount Friday. What happens there is then we would look up the value of discount Friday in your globals JSON that you provide to the indexer agent. And we can see there that in the globals on the right, discount Friday is true. So this statement would match all queries, and all queries would have 0.0001 GRT. I could think of maybe using something like that for if there was a conference coming up and you expected there to be a lot of load, and maybe you want to apply a discount for a limited time, say. The next example would be an example of using database statistics in order to inform the price. So you can see that it says, give me entities where the ID is greater than a specific ID. And maybe the cost of that query would actually scale with the number of IDs that are in the database. So we have an expression after that that says use entities times 0.00001 GRT. We would then look up what entities is in your globals table, and we see that it has the value of 250. So then a result of a query that matched that statement would be 250 times 0.00001. So in that way, well, you'd be able to pipe information in real time from the database as new blocks are being ingested by your indexer, and quickly update your prices without manual intervention. All right, so maybe that's something that you want to take into account. It's up to you. A third example here would be using the load factor on your server to update the prices. Perhaps you see that load is changing over the time of day, and you might want to restrict the amount of load on your server, or maybe if you have low load, to try to attract more queries. So we can then see that this third statement is just using load factor directly as their price. We could look that up in the globals and see that load factor. I'm sorry about that. I tried to move the. I can't actually see what load factor says because Zoom's camera thing is in the way. So whatever that says, it would look it up. I tried to move it out of the way and it went to the next slide. So I'm just going to keep talking. All right, so it would look up whatever load factor says and use that as a price. And then you could dynamically detect what kind of load that you're under and update your price accordingly, maybe to attract more queries or to try to reduce the load on your server accordingly. There are many different uses for globals. These are just some examples to get you thinking about how you might use them. All right, so once you've developed a cost model, the next thing that you're going to want to do is to test it before rolling that out. And so we have some tools to help you do that. After this slide, and in fact, the last slide, I have some links that are going to show documentation for all of these tools, so that you don't need to furiously try to write down these command line things right here. Instead, I would encourage you to look up the many options that these tools offer according to their documentation from the last slide. So in order to evaluate your cost model, what you're going to do is first to save some set of queries that you want to evaluate. And the way that you can do that is by setting the graph log query timing environment variable to the value GQL, and that's going to start saving some queries to your logs. The next thing that you want to do is to run a tool called qlog to pre-process those queries. It can do things like extract the queries from the log. It can filter by specific subgraphs. It can take a specific number of samples of queries so that you can iterate more quickly. So you'll want to run that using the next statement here, which greps logs for query timing and then pipes that to qlog, and that will output this queries.jsonl file. You'll then want to store that somewhere so that you can iterate on your cost model and try running it several times over on the same set of queries. And then the last thing that you want to do is use the Agora evaluation tool to run over all of those queries with your given cost model and your globals, and it will output then how many query fees that you would have accumulated in the aggregate based on your logs. So that will give you a way of figuring out whether or not you're meeting your revenue targets, say, for a given set of queries over a given amount of time. It's not going to be totally accurate because, of course, the actual price that you specify for your queries is going to affect the queries that you receive. So it's not a prediction in any sense, but it's better than nothing. And so go ahead and test your cost model using this. Once you're satisfied with the results and you'd like to deploy your cost model, you can use the indexer CLI for that. So there's one command in the indexer CLI for setting the variables, which you are expected to do fairly frequently and according to changing market conditions, changing database, changing whatever. And there's also another command for setting the model itself, which you're expected to do a bit less frequently because that would usually require human intervention and a changing strategy of how you want to do your prices. Again, links to documentation are going to be on the last slide, so you don't need to memorize this. But there would be these two commands in the indexer CLI that you would use to deploy your cost model. So the set variables is going to be a JSON file, which contains all of the global variables that you want to use in your cost model. And then the set cost model is going to be an Agora file, which contains all of the list of statements that I showed examples to you of earlier. So that we've looked at Agora and we've seen how to communicate your prices. But that still leaves a pretty big question that's on everyone's mind, and that is, what should you set your fees to? I'm not going to, during this talk, anchor query fees to any particular value because I think that would do the community a disservice. The network is going to be comprised of many independent agents that are all acting in their own best interest, right? That includes DApp developers trying to minimize the price that they are paying for queries. That includes indexers trying to maximize the price that they're accruing from queries. And I have no inside knowledge of what any DApp developer is willing to pay. And I have no inside knowledge of what an indexer would charge for a query. But I can tell you how I might frame the problem if I was running an indexer. And I can hope that that would be helpful to you as a starting point. So if you remember at the beginning of this talk, I said that many things can go into the price of a query. Right? There are many factors. One would be what differentiates you as an indexer. Did you splurge for that low latency database and do you need to recover that cost? Does the subgraph that you're serving have a high query volume? Does it cost a lot to index it? Right? Do you need to make many Ethereum calls, say, to get that data from an Ethereum provider? And what is that going to cost you? So I'm going to make the case, though, that when setting your optimal price, that none of these factors are your primary concern. When you are setting the price, there's actually only one question that really matters. And the question is, what price maximizes my revenue? The indexer's revenue is going to be the price per query that they set multiplied by the size of the market that they can capture at that price. And the size of the market that you can capture already takes into account all of those other questions that we were thinking about when talking about query fees earlier. The size of the market that you can capture takes into account what differentiates you as an indexer compared to the pool of available indexers to select. The size of the market that you can capture takes into account whether you splurge for that low latency database. And then the revenue function is affected by the size of that addressable market. But then all that's left after taking all those things into account is what is going to be the price times the market captured, and making, or rather like getting as much revenue as possible out of the market that you can capture, taking into account that the price that you set also affects the size of the market that you can capture. So once you figure out your revenue maximizing price, then you can decide which query markets are the most attractive based on your expected profits. So I think that can kind of simplify what you're considering when writing your cost model. But then it makes it a bit of a more interesting question when you're deciding which subgraphs to index, based on how many other indexers are indexing this subgraph, based on what is the query volume, and all these other questions. Excuse me. Once your broad strategy is established, actually, sorry, that's for another slide. All right. Okay, I want to hammer this point home about maximizing revenue. Let's see, can we get this to run? No. How do we get this? There we go. Okay. Technical difficulties. I apologize. Okay. So figuring out that optimal price that maximizes your revenue itself isn't going to be very easy, because the optimal price depends on your quality of service that's relative to the quality of the service offered by all of the other indexers, as well as their prices, the full set of consumers, their selection preferences, their budgets, the amount of volume at the current time of day, how much load your server can bear, the gateway selection algorithm, and probably the phase of the moon. For all that I know, it can take into account a lot of different things. For our gateway, an indexer which offers a better service does have a higher revenue maximizing price. So to drive this point home, I want to show this graphic, which demonstrates a graph that shows the expected revenue at different prices relative to a consumer budget for given our indexer selection algorithm at one point in time. So what you're looking at is a graph that shows on the x-axis a price that the indexer could choose as a proportion of the maximum price that the consumer is willing to spend for a query. And then on the y-axis, it is the amount of revenue that the indexer would actually receive for that query. And over time, I'm increasing the amount of utility that the indexer brings to a network, right? By say making them a better indexer, by having better economic security or better performance or what have you. So what I want you to notice is that by increasing the utility that you offer, that is going to have a pretty large effect on the amount of revenue that you can bring in. So as time increases, that graph is getting higher, which means that we're bringing in more revenue. But also, as your utility is increasing, that the price that would maximize your revenue is also increasing. And so that's represented by that the vertical line that's intersecting the curve at its highest point. That is your revenue maximizing price, because it captures the most revenue when multiplying the price for that query by the size of the addressable market that would be captured at that price, right? As you increase your price up to and beyond the maximum that a consumer is willing to pay, that can drop to 0. But as you decrease your price, it also goes to 0, because even though you're capturing more queries, you're not actually making as high of a price for that query. So what you want to do is figure out how to discover what that revenue maximizing price is going to be. An idea that you might use to figure that out is actually just to go back and use global variables. I could imagine having a global variable that's a multiplier for all of your prices, so that you can adjust it and see how it affects the market that you capture, as well as how that will impact your revenue, and just kind of try and discover this information. That's an idea. There are many ways that you might go about this, but that's probably the way that I would do it if I were an indexer. Going back to questions about pricing strategy, once the sort of broad revenue maximizing strategy is established, Another thing that I might try to do with cost models is to use Agora to disincentivize very long running queries that need to be optimized. So what we've observed in the hosted service is that many queries go very fast, but there are some queries that might take 5, 10, 30 seconds to evaluate because of the complexity of the query or the amount of data that they're requesting. So you would want to raise prices on those queries, which would incentivize the app developers more than they are already incentivized to optimize their queries, so that those queries can be executed very quickly and not bring excessive load to your server. But also you can raise prices on those queries so that those bad queries can be routed to competing indexers and become their problem and a problem for their infrastructure instead of yours. So that might be another way that I would use Agora. Agora isn't necessarily finished. And in fact, one of the things that we wanted to do during the testnet was to be able to see how that indexers priced different queries and figure out what strategies emerged, and then to update Agora over time to be able to express those strategies more efficiently. But it was not something that we really had time to during the testnet. But because this is extra protocol, we still have room to iterate on this design. So ways that we might iterate it include that because you can list every possible query and price each one individually using Agora, it is possible to express any possible cost model logic that you could imagine. But the downside of that would be that the cost model would get very long. So what we want to do is to, within the design space of Agora, give you that flexibility right now to be able to experiment and come up with any cost model that you can imagine. And as patterns emerge, as we see that indexers are doing the same things over and over again, offer new language features in Agora that would allow you to semantically compress the resulting cost model and express your strategy more efficiently. So you can see that the captures that I talked about before are one feature along those lines, which can take many different possible queries, reduce those to a single pattern, and then make cost models shorter. Similar ideas can be introduced over time once the community is more comfortable with the best way to express their strategies using Agora. So, please open issues on the Agora repo, give us feedback, and we'll try to make this, a great tool for you to use over time. Lastly, if anyone has any questions, it looks like we have about 15 minutes for questions. And here are the promised links to various pages of documentation so that you can look at the options of those different command line arguments that I went over earlier, and figure out the full feature set that's available to you. Also in the Agora, make sure that you look at the language reference, which is going to show every possible way that you can use the language. It's a bit technical, but once you have the idea of what broadly how Agora is used, which I hope that I've communicated in this talk, then that will give context to the way that you might be able to use those language features. And of course, feel free to ask questions on Discord as well. If you then look at this documentation or are confused for any reason, ping me on Discord and I'll get back to you. But right now we have, again, 15 minutes for questions if anyone wants to take the floor.
Hey, Zach, awesome presentation. My head is very slightly sore, so thanks for that. Question about default arguments and how they are matched against Agora rules. So for example, if you do not specify a first argument in the GraphQL query, it obviously still defaults to a value. So how are defaults mapped to rules in Agora?
That's a great question, and Agora does not have knowledge of the default arguments. I think that would be a great thing to add. So let's open an issue on GitHub for that.
Cool, thanks.
Thanks, Zach. I was only here for the second half, unfortunately. I was in another meeting, so forgive me if this is covered in your first half, but I'm just sort of thinking about, right, the input side of Agora. Back in the early days of the mission control, when we were all sort of experimenting with the price thresholds, I often sort of compared it to, you know, stumbling around in a dark, pitch dark room looking for a light switch, right? Mm-hmm. So we don't have the visibility that hosted has, right, to see the queries there. We, you know, and on the main net, you know, just thinking as an insular indexer, you only have knowledge of the queries that you are getting. So in this new world that we're moving into, you know, I can see in terms of the data a need to do things like sharing data, right? Because I'm assuming that we're still in that same situation where we're not being told how much how much consumers are willing to pay. We have to work out how much consumers are willing to pay. So can you talk a little bit about your thoughts around that side of the market, I guess, query market?
Right. So there's a broader question there, right, about just how are signals about the broad market going to be shared in a decentralized way without, allowing for fraudulent behavior, right? How do we ensure that an indexer could share information about the market? How can consumers share their information about their preferences and so on and so forth? That is a question that we've been thinking about a lot. I don't think that we have a good answer for that generally. So right now, each participant in the network is going to be limited in their decision making based on what information that they can see until we figure out how to broadly expose market signal to all of the participants. So right now, I would just encourage you to take active steps toward gathering information, right? So one thing that you can do is set your prices to 0 and see then what is the size of your addressable market in the maximum. This is not something that you would leave running for very long, but you can probably afford to do it for an hour. And then you'd have a decent set of queries that at least meet the minimum threshold for what your indexer offers otherwise in terms of, say, economic security and performance and these other factors, and then figure out what your revenue maximizing price is from there. So until there is a global market signal, then you're going to have to investigate information.
There's a question from Vladimir. He sent me asking, is it possible to get a list of available global variables? And how can he add custom global variables?
Yep. You can use, there's only one sort of magic global variable that's automatically injected by the indexer agent, and that is the conversion rate from DAI to GRT. All of the other global variables, you come up with their names, you put them in a JSON file, you come up with their values, you put those values in the JSON file, and they're just supplied via the indexer CLI. So you have total freedom as to what you want to use for global variables.
Somewhat confusingly, globals seem to be subgraph specific, as in when I define a cost model, I also attach the globals that apply to that model specific to the subgraph. If we were to implement kind of more holistic global space strategies, for example, something like load targeting, is there a true global, some way of defining like a system load level that applied to all cost models, or would we need to loop through each of the, subgraph deployments and set the globals individually?
Right now, you would have to loop through and set the globals individually. With some globals, like say the entity count, that could be information that is different per subgraph but may have the same name. So we don't expose a way of having global variables like a hierarchy of global variables. I think that could be an interesting feature, and that's something that we could add to the index or CLI to say merge global variable documents. Yeah, I could see that being useful, but we don't have it right now.
Cool, thanks.
Any other question? Anyone that wants to jump in to the stage? Okay. Guess if not, we can take the time back. Do you want to cover something else, Zach?
I don't have any more content, but thank you all for coming.
Okay, thanks everyone. I will be sharing the recording afterwards. Bye.
Bye.
Thanks.